Okay, good morning. Glad to see everyone actually made it here for 9 o'clock. What with being here late last night, it was kind of a bit of a struggle. For me, anyway. So, my name's Ade Miller. I currently work for CenturyLink Cloud, where I stare down large distributed systems written in a mixture of languages, none of which are C++. Which brings me to my next slide. I'm not a professional C++ programmer. How many people in the audience don't program C++ for money? Oh, a few of you. Actually, quite a lot of you. Wow. So you're fans of the language like me. I rediscovered C++ a few years ago when someone told me I had to take a book I wrote in .NET and write a C++ version. So I went and bought Scott Myers' books and brushed up on my C++, and here I am now. But largely I do this for fun. I have had a sad sort of affectation with n-body modeling since I was about 12. So I started writing n-body models on GPUs and discovered they were really fast. So that's kind of how I got where I am today and why I'm standing here talking about GPUs. So we're going to cover a bunch of stuff in this talk. I spent a lot of time hanging out on the Stack Overflow forums and answering lots of questions about parallel code and in particular C++ AMP. And I was kind of horrified because we wrote this book on it and people are asking these questions that clearly we should have answered in the book or didn't explain real well. And it sort of struck me that really it's very easy to kind of do GPU programming 101, which we'll cover. How many of you were in Mark's talk yesterday? Okay, so a few of you. How many of you are familiar at all with C++ AMP? Okay, again, a few of you. So this talk is really about algorithms. I'm just going to use C++ AMP as my language of choice to demonstrate it. But the goal is to think more about the underlying algorithms and how you would actually take something that you wanted to do and get it to run on a GPU rather than like just rely on somebody else's code or take one of these really trivial problems and get it to run on a GPU, which is not really that difficult. And I wrote a bunch of the case studies and all the samples for the book. I've written other things. I'm doing some work on a library that sits on top of C++ AMP called the AMP Algorithms Library, which is a bit like Thrust, if you're familiar with CUDA, or the STL or parallel STL, or what have you. What we're not going to get to today is how to be a performance guru, or like all of the deep dark secrets of GPUs, of which there are many. There just isn't going to be time. But I'm hoping to get you to the point where some of the things that maybe you kind of struggle with today are a bit more tractable and easy to understand. And I sort of have this algorithm family tree type thing going on. So when I looked at what I was doing with the AMP Algorithms Library, it turned out there was sort of this little hierarchy of things you needed to build. And today we're going to look at transform and reduce and in slightly less detail at scan. And it turns out these are kind of these building blocks that you kind of have to build if you want to build a library, and they also encompass a lot of the techniques that you're going to need if you want to write your own more general algorithms. Some of the ones I'm not going to cover, for instance, is generate and fill, which are essentially rather like transform in that they do essentially one-to-one mappings. So if you were in Mark's talk yesterday, we kind of saw a little bit of what you can do with a transform or a map. Turns out, really all you're doing here is you're applying some function to every element in a vector. You can do this really simply in the standard library using transform. You can see in the example code here, I've created this functor called doubler. The slides I'll be putting on my blog at the end of the presentation if you want to grab them. So I've just declared a functor up here that just doubles the input. And I've created a vector, initialized it, and now I'm going to call transform on it. So that's going to give me what I want. Really trivial and embarrassingly parallelizable, right? There's no dependencies between different elements in the array. So if I were doing this on a GPU, it looks like this. I want to introduce these diagrams to you because you'll be seeing quite a few of them. They're the best way I know of to kind of understand what's going on with one of these algorithms under the hood. So in this case, the boxes represent locations in your vector, your input and output vector, and the lines and the little pluses represent operations. Note they don't have to be additions. In this case, they're my function f of a. Across the top, you've got the index, which is the overall index in my array. As we'll see in a minute, you kind of have to keep in your head several different indices when you start dealing with the more complicated algorithms. Is everyone following so far? Are we all good? I know it's a bit early in the morning. So what does that look like using C++ AMP with the AMP library? So this is kind of, for those of you who aren't particularly familiar with C++ AMP, this is kind of the primer. So C++ AMP provides you with this keyword extension on the language, restrict. What that allows you to do is specify that you would like a particular function or lambda to be compiled for different targets. And tells the compiler that you want this to run in different places. So here I've targeted it to run on the CPU, so I could still use it in my original STL algorithm. I don't need to go change that. And I've also asked it to create me a copy for the GPU. Right? AMP, when I say GPU, AMP actually doesn't have any real notion of GPU. It has a notion of an accelerator. In principle, the AMP model you could use to target other accelerated devices. And in fact, you can already target GPUs and a software accelerator that runs on the CPU with it. So that's all I have to do to this function because it doesn't use any types that are not usable on the GPU. So GPUs don't typically support all the same types that you can use on a CPU. For instance, a large majority of GPU hardware will not support double precision. But I'm okay here because I'm only using ints. But I could be using floats, unsigned ints, what have you. The next thing I do is I do exactly what I was doing before. I initialize my array on the CPU. So there's no difference there. I'm still using std vector, and I'm creating an input and an output array, right? So that's all the same. The magic happens here, where I set up these two array views. Now, an array view is a wrapper around my host memory, around those std vectors, right? So what this allows me to do is transparently and lazily move data to and from the GPU. So this isn't a copy, it's just a wrapper that I've declared. And then I'm going to use the AMP STL algorithm here. So again, now I'm just passing it in these input and output array views and my functor. So what's actually going on under the hood? What does transform do? Because transform is pretty trivial. So all transform's really doing is it's taking my doubler functor and it's passing it into this overload of parallel for each, which isn't really that different from the parallel for each that you would use on the CPU. All I'm really doing here is instead of passing in an index, I pass in a property of my view called an extent. Did anyone go to Lucas's talk yesterday on extending C++ with arrays? No? Okay, so there's a proposal to put array views into some future version of C++. The nice thing about array views is they're multi-dimensional. So you can use them to encapsulate any sort of array and say, well, this is a 2D array, even though under the hood all my memory is contiguous memory, just like you do today with vector, but you have to do a whole bunch of sort of funny math, right? So I'm actually using an index of 1 here, and I have a one-dimensional array. And again, I'm marking this lambda restrict amp, right? That means that it'll run on the GPU. And then, really, my code inside there is exactly what you would expect. I'm saying that the output should be the input passed through the doubler functor. Does that make sense to everyone? Okay, so the other interesting thing I'm doing, so this is your like hello world equivalent in the GPU world. Some people use a more complex function here. You'll often see SAXP used, which is it's a popular, like really trivial sort of finance type algorithm. But essentially, this is hello world, right? What happens here with my array views is, remember I said they were wrappers, they weren't explicit copies, is this code is all, you have to consider this code asynchronous. So when I fire off my parallel for each, nothing actually necessarily happens. It just gets queued to the GPU, right? Under the hood, AMP will not only queue this, but also all the things that depend on it, right? So that will queue the copies of my array views where required. If I access or call an explicit synchronize on my output array view, that's the only time I'm actually guaranteed I'll have the result, right? So under the hood, there's all this sort of, fanciness going on to move data in and out and to do it efficiently. Now, we're C++ people. I just told you you'd lost all that control and now you're not happy, right? I certainly wasn't happy. So there's another construct here you can use called array, which I'm not going to deal with today, but array actually represents data living on the GPU. If you want, you can use array and you can use explicit copies, you can use explicit async copies to get the fine-grained control that you want. Okay, so we're going to talk about array views exclusively today just because it's easier to deal with, it's less code. If you want, you can do all the copying yourself, and there are sometimes good reasons for doing that. The other thing that you might have thought of about array view is, and this is kind of the first thing you should think about when it comes to designing your code, is that, well, hang on, I've got this input, right? Well, I only care about it as an input. Why would I care about it after I'm done with it, right? So, and similarly with my output, I really don't care what's in my output when I start. I know I'm going to write to every element of it. So C++ AMP supports this notion of a const array view, which means, hey, this is a constant. I'm guaranteeing I'm not going to change it inside the kernel, so don't bother copying it back out, right? So I've just saved 25% of my copy there. Same with the output. I can call output a view discard data. That says, I don't want to copy the output view in. Just ignore this data for now. I'm only going to copy it out, right? So I've just halved the number of copies. And that's kind of one of the first lessons that you should think about when you're designing things that run on GPUs, is copies into and out of the GPU, particularly discrete GPUs as opposed to integrated ones, tend to be very expensive. So when someone asked a question yesterday, what's worth doing on the GPU? Should I do something with 100 ints or, 1 million ints? The question should really be, am I going to recoup the overhead of the parallel work? And that's actually just as true on the CPU, right? Am I doing enough work such that if I introduce an overhead in parallelizing it, will I get that back, right? And you can see examples of people doing this on the CPU where they parallelize something that's really trivial and it actually gets slower because they're doing more work trying to track all those threads or tasks or whatever than they are actually gaining by running on more than one core. So the same applies here. In some respects, this would not be a good example, right? Doubling a bunch of numbers, even if you had an awful lot of numbers, you've still got to copy them all across that memory boundary onto the GPU. What you might want to do, if you were using this, you might still want to use it as part of a larger kernel or with a much more complicated function. So Mandelbrot, for instance, is actually a pretty good example because you can, it's a much more complicated function. Sorry, question?
I was wondering about the input view. Can you restrict it to only a subset of an array? Like an input vector at that point?
Yeah, so the question was, can I restrict it to a subset? Yeah, there are two ways I could do that. I could actually declare the array wrapper as a subset, or I could use section on my array view to subset it down. The nice thing about section is if I have a two-dimensional array view, I can subsection a two-dimensional block out of that array view. I mean, the really nice thing about array views and arrays is you can get rid of a lot of this nasty math you tend to see in GPU code where you're trying to map from your problem domain, which is n-dimensional, into the flat memory domain of the device.
And then the second one, the restrict keyword here, you said it restricts it to running on the GPU. Is that meaning that you could also restrict it to running on the CPU? And then thirdly, could you just let it go wherever it wants to go?
So the question was, how can I use the restrict keyword? Can I restrict it in other ways? So if I say restrict AMP or restrict CPU, that is an only scenario, right? That means it will only run on that. If I try and run this on the CPU, I will get, if I went back and I tried to create a restrict AMP only lambda and tried to run it on the CPU, it would fail, right? There is no anywhere. You have to specify a list. So you will see people specifying AMP and CPU, right? And in principle, there's nothing to stop the standard being extended to add other things. I should get going, because otherwise we're going to run out of time. So reduce. Really all we're doing is summing a bunch of numbers here, right? You can see this in the standard library as accumulate. Is anyone going to shout at me now? No? So accumulate and reduce are not technically the same, right? This is one of the things that trips people up when they start parallel programming, regardless of whether they're doing it, right? The semantics of accumulate are that it is ordered. The minute you start running things in parallel, the order of your operations is no longer defined. So reduce requires that the operation you are using is associative, right? Because you cannot guarantee the order at which in this case, the additions are going to take place, right? That gets really nasty if I were trying to do an accumulate and map it to a reduce and I was using matrices, right? You cannot do that with matrices. Matrix math order matters in many cases, right? So this is something to beware of. This will lead to small errors if you were to try and compare the results of a sequential and a parallel implementation of this, you would see small rounding errors. You're looking at me funny. Okay? It's true, right? If you take two floating point numbers and multiply them, and then multiply it by another one, and then switch the order, you get rounding. That's not true of real perfect numbers in the real world, but it is true of numbers when they're stored in a computer.
It's worse when it happens.
Yeah, exactly. Any of those operations, don't expect it to be quite the same. So what does reduction look like? So remember now I'm not doing this simple transform, I'm trying to go from many numbers to one number. So this is the trivial way of doing it, right? I basically split my array into two halves. So I've got 16 elements here. I'm going to use what I call a stride of 8. I'm going to add the first one and the 8th one, the second one and the 9th one, and then I'm going to halve my stride. So now I'm going to add the 1st and 4th. I'm going to halve it again, and I'm going to halve it again. And magically at the bottom you see 136. 136 appears a lot in this deck. Okay? So again, this is all in global memory. So you'll see later on, blue boxes represent global memory, and we'll go into that in a minute, right? So the first thing you might notice about this is that I'm only using some of the threads some of the time. What does this actually look like in code? Well, it's actually pretty trivial, and it sort of boils down to something that looks, fairly familiar to the code we were looking at before, but now I've wrapped it in this loop that keeps halving the stride each time, right? So I keep adding up, basically keep folding the array back onto itself till I've got nothing left, right? And again, I don't have any contention issues here. I'm not trying to sum a single number, right? Typically you'll see people when they try and write parallel code, they'll say, well, I want to do a sum. Well, I'll take a total and I'll surround it with a lock, and I'll lock on the total, and then I'll add all the numbers up from threads, and they've basically just written the most complicated sequential loop that they ever could, and it doesn't perform very well. AMP does support, well, AMP and GPUs in general support the notion of atomics. I try not to use them wherever possible. So there are actually a couple of problems with that code. The first one is that it's not using tile static memory. All my boxes are blue boxes, but I'm doing lots of reads and writes to global memory. That's just the same as if you managed to write an algorithm on your CPU that somehow avoided all of the cache lines and all the L1 through L whatever it is now caches, right? The performance wouldn't be that great, right? The second problem is that, as you saw, most of my threads aren't doing anything. The only time I use all my threads is when they go, get that first piece of memory, first value, and do something with it. So it's kind of not so great. So for those of you who were in Mark's talk yesterday, we sort of touched on using tiles and tile memory. I'm going to use the word tile here. If you're familiar with CUDA, NVIDIA uses the word block to mean the same sort of thing. This is a very simplified view of how a GPU is doing things under the hood, right? It happens to work as a sort of it's the mental model I use to try and figure out, what is happening with my algorithm. But do not take it as gospel. Things change all the time. For instance, NVIDIA now has some forms of caching on their latest GPUs, right? We're not going to consider that. So what happens here? So I have a kernel. That's my little restricted AMP lambda. That might have millions and millions of elements in it. I'm saying, do my function on all these elements. The problem there is that I might have a GPU in my laptop with, I don't know, 1,000 threads available. And I might have a GPU or 2 GPUs in my machine at home with 5,000 for the sake of argument, right? I have to be able to break my problem up into chunks so that I can schedule those chunks onto the GPU. So I break my problem down into tiles. The original code we saw didn't use tiles because C++ AMP will do that for you under the hood. And then the GPU processor breaks things down into warps, right? So warps are typically blocks of execution that are typically think of them as 32 operations wide. right? So when I schedule my algorithm, it gets broken up into these tiles. These tiles get executed. There's no guaranteed order. Tile 1 might not execute before tile 4, right? And then those get run as warps. Now, the threads within a tile, there's also no guaranteed order. The only place I'm actually guaranteed order is in those 32 operation-wide warps. They occur in lockstep. Remember that because we're going to come back to it. So that was sort of how I schedule things. What does my memory look like? Well, I've got this big block of global memory. Typically, a GPU today has several gigabytes. Tiles get scheduled on what NVIDIA calls a symmetric multiprocessor, or SM. I'm scheduling these tiles. I'm trying to hide latency. There are only certain things that I can synchronize here. So I have barriers that we'll be using later. I can synchronize access to global memory, but only with these limited atomic operations, which we try and avoid because in general they're expensive. Tile memory you can have barrier primitives within your tile or block to allow you to say, well, I want to wait here in this tile until everything has got to this point, which you'll see comes in super useful in a minute. But remember, the tiles may run in any order. And I also have registers. We're not really going to get into this today, but you'll hear people talk about occupancy. The deal with occupancy is that a symmetric multiprocessor, of which you've got of the order of sort of 10 or 16 or something on your GPU, has a limited amount of local tile memory and registers and threads. If you break your problem up such that you use too many threads on a symmetric multiprocessor, you may discover that you're leaving a bunch idle. So for instance, suppose each one of your SMs has 512 threads, and you decide that for some reason you want your tile to be 513, which is a ridiculous number because it's not divisible by 2, but so that means that I will schedule one tile on my multiprocessor and I will leave all the other cores just hanging out because I can't schedule another one. So that would give me an occupancy of 50%. Similarly, if I use up all the memory with one tile, I can't schedule any more. So you'll see people worrying about that quite a lot. You'll see people talking about occupancy quite a lot. This is one of the things I'm not really going to dig into very deeply today, but it's something to be aware of. So how do I use tile memory? Okay, so same sort of diagram, and I have a couple of other things going on. Green is tile memory. Green is good. Blue is my regular global memory. When I use tile memory, I now have 3 different indices to keep track of for each element. I have my global index, which is just what we had before. I have my tile index. Here I have 2 tiles, 0 and 1. And I have a local index within each tile. So the first thing I'm going to do is each of my threads is going to load memory, load into tile static memory, right? So this is a bit like if you actually had to go and manually load your L1 cache. If you were at the author's talk yesterday, I said to someone, if you want to go write your own cache controller, this is the way to do it, right? Effectively, you have much more explicit control, which is both good and very bad, right? I'm then going to do exactly what I did before. I'm just going to keep summing these things until I get my final results for each tile, which in this case, I'm going to copy off into global memory. Okay? So you'll notice here that I've solved the tiling problem, but other than that, I have not solved any other problems in terms of I've still got a lot of idle threads. So don't read the code. I said don't read the code. So what I want to focus on here is this is a really, really common pattern you will see in tiled GPU code or blockwise GPU code. I'm going to create an array for storing my per tile results, but really within my kernel, all of my all of my threads load data into tile static memory, right? That's all they do. There's a one step there. They then wait on a synchronization primitive. Then they do a whole bunch of work and they calculate the result in tile static memory, and then they wait again, right? The waits are important because I don't know what order all the threads are going to execute in, and if I start to read from memory that I haven't yet finished writing my initial values to, it's not going to go so well for me. And then finally, I'm probably going to write the data back to my global array. So what does that actually look like under the hood? So if you focus on where I've highlighted tile data, here's my load everything into tile static memory, right? And then I call tile barrier wait, right? Tiled, I'm using a thing called a tiled index up here. Tiled index have some additional features as well as providing me with global and local tile indices, those additional two indices that I had. They also provide me with these barrier primitives. So I'm now guaranteed that everything within the tile is at the same point, which means when I start doing things with my tile static data, I know it's all been loaded. Without that barrier wait, bad things happen, which normally means you staying up really late because you'll get non-deterministic results out of your code. Just don't do that. Then I'm going to do a bunch of work in here, and then I'm going to use the first thread, right? So tile index 0. See here I'm using tile local 0. So that's the first thread in each tile is going to copy the result out into the global array, right? And that's okay because each tile is going to copy data to a different place in the global array. I don't have any contention, right? You really don't want to be writing algorithms where you've got a lot of global memory contention. It's just not going to be very performant, and it just gets to be a headache. We'll see in the next few slides, a lot of the changes that we make to this code to make it perform better are not huge changes. They're subtle changes to the way, to where we read and write from and which threads we execute on.
So,
question?
Sure, I understand. So in the work loop, or the work part of it, you have, each time it goes through, half the threads just essentially fall through to the barrier fence, to the static memory fence. Essentially, there's nothing for them to do.
Yes, so the question here is are actually all the threads doing any work? And the answer is no, we still have this problem where half the threads are sitting around doing nothing, right? Because of my stride statement here. Half these threads are not going to meet this condition, right? And we're going to come to that in a minute because it's actually bad for other reasons. And what I'd like to do is reduce the number of idle threads. So the first thing I want to do before we deal with that problem, which as we'll see is actually a worse problem than just half the threads doing nothing, I want to have a go at reducing the overall number of idle threads. And remember, most of the time, there's like at that first level, half my threads, all they do is load data, right? They don't do any work. They just go get data. So the solution to that is, why don't I have every thread load from two places and do an operation, right? So make that first level a load and reduce rather than just a load, right? So I'm going to do this for each thread, and then we're back to where we were before, all right? So that's just one tile, right? So there are essentially more little plus operations on the diagram than there were before. This is generally good, although we'll see in a minute why it might not be. So that's reduced the number of idle threads I have, right? Simply by virtue of the fact that I'm no longer just doing a load. I'm going to do two loads and an add for the first set of threads. What does that look like? It doesn't really look a lot different. This is the load part of my algorithm. Instead of just doing a load here, I'm calculating the other offset and I'm loading another value. Okay? So again, this is one that wasn't a big change to the code, but it's going to make a big difference to the amount of compute you get out of this, right? You know, you've now got half the threads that did do nothing doing work. So you'd expect that to be a big perf improvement. All these samples, by the way, are taken from the book that I'm going to shamelessly plug at the end of the talk, which includes timing results. We spent a great deal of time and effort making sure that in the chapter we wrote on how to do a reduction, we weren't lying to you and things did actually get faster. However, we've created a couple of new problems for ourselves. The first is, you mentioned that conditional. We've got a tight loop with a conditional in. That is not good, period. I mean, it wouldn't be good on a CPU. So as a C++ programmer, I'd be thinking, well, I probably don't like that very much. And I'm only going to touch on this peripherally in the interest of time, but our memory access patterns are not particularly great either. So here's the code that we have, right? Every other thread does an operation. So there are all these like white circles there of threads that are not doing anything, right? So that's bad, right? We've tried to solve that to some extent by having all of our initial pass do 2 loads and an add. But this is bad for another reason. Remember I said that everything gets divided down into these 32 operation-wide warps that get scheduled? Well, it turns out that all the warps execute all the code, right? So in this particular case, every warp is going to get here and it's going to evaluate this conditional, and if it's true, it'll go on and execute this statement. If it's not true, it's basically going to incur the cost of executing this statement, right? So remember, I'm trying to schedule warps as fast as possible. Well, now all my warps are going at the same speed, which is the slow speed, right? I'm not getting half of those threads finishing in no time at all because they went, oh, I got no work to do, right? So what I would like to do is end up with 2 sets of warps. The set of warps that does all the work and the set of warps that does none of the work, right? It's a bit difficult to see here because my tile is 8 wide. If my tile was, say, 512 wide, which is a completely reasonable number for a tile, I'd be executing many, many warps, right? But they would all be slow. What if I do this? Right? Now, the lower half of my tile, all the warps are going to take the path where the index evaluates to true and they actually do work. All the warps in the upper half of the tile are just going to fall through because now they're all evaluating this the same. Right? Does that make sense? You can think of it a little bit like the vector instruction set on the CPU if you've ever used like SSE. Another question.
Can you go back to the previous slide?
I can try. Oh yeah, there's even a button down here for that. Right? Here I'm just evaluating odd even effectively. Right? So nothing has changed in terms of the work I'm doing, it's just where I'm doing it. Does that make sense? We can talk about it afterwards. I kind of have to plug away at this because I don't go over time. Right? So the final thing that I want to do is deal with a little bit of this memory access pattern. So it turns out that the way that the memory works in tile static memory is it's arranged into banks. And in a memory bank, you either want everybody reading the same value or everyone reading from different banks. So the best way of doing this is, in this case, is to move your reads far apart, right? So it's a bit difficult to see here because I couldn't show you a tile with 512 elements on it. But all I've done here is, again, do a little bit of reordering to make those reads further apart, which means that I will tend not to read from the same, I won't be reading different things from the same bank as much, right? I'll still be doing it, but not as much. Again, I don't want to go into this in a great deal of detail, but memory access patterns are kind of the next level of thinking about GPU algorithms. It can kind of get a little bit tricky. People do tricks where they, introduce essentially off by one indices because that causes things to not repeat over the same bank, for example. But again, this is another sort of subtle little thing I've done just to shuffle the ordering around a bit. It's not a huge change to the code, but it can make a big difference in terms of performance. So, should you all dash off and write a reduction algorithm? No. There's one in the AMP algorithms library. CUDA has a very similar library called Thrust, which contains many of the same algorithms. I'd like to remind people that a lot of the time when we talk about things like parallel code, we show them matrix multiply. If you want to do fast matrix multiplies, there are libraries written by really frightening people at places like Intel and NVIDIA that will probably beat the perf of yours. So the other algorithm I wanted to touch on, and I'm not going to go into this in as great a detail, but I wanted to touch on it because it's another one of these things that people kind of start to struggle with, where it doesn't seem to initially map to the I have an input and I have an output and I just transform data between the two, right? So we dealt with one-to-many. This is a many-to-many mapping. For those of you who aren't familiar with scan is basically summing all of the numbers, all the elements in an array where the answer is all of the sum of all the previous elements, and with inclusive scan that includes the current element. Exclusive scan does not. So you can write that really trivially in C++ today, in hopefully moderately modern C++. So what does that look like? How would I do that on a GPU? Well, it actually turns out it's not so bad, even though the answer for the number at index 1 depends on the answer from index 0, right? I can do it like this. So essentially, it's another one of these folding operations. It's really interesting, actually. Some of the papers on how to do these sort of operations on a GPU actually go back to almost before I was born, when people were playing around with sort of very, very early SIMD parallel machines. The algorithm on which scan was originally based was written by Hillis and someone else, and it was designed to run on a connection machine, which is one of these high-performance computers from days of yore that did a gigaflop or something. Back when that was considered insanely good. So here, this seems good, right? I'm doing lots and lots of work. I don't have a lot of threads that are hanging around doing nothing. Turns out I have the opposite problem. So sequential scan is order n, right? I just keep adding numbers going through the array. I've just written something that's n log n, which is not as good, really. Now, as a quick and dirty solution as part of your algorithm, it might do the job. It might still be faster than moving the data back to the CPU, for instance, doing a scan on it there, and then moving it back to the GPU and continuing. There are several things. Another good example is histogram. There are several things that are actually pretty hard to write on a GPU, but just as I said with a parallel algorithm, the overhead, you have to negate the overhead of parallelizing it. In some cases, on your GPU, you might want to do something that's not particularly efficient on the GPU, because that's better than copying it to the CPU, figuring out what the answer is there, and then copying it back to the GPU, right? And histogramming is one of the examples that NVIDIA used to talk about, where histogramming wasn't easy on a GPU, it wasn't super performant, but if you wanted a histogram, it was better to do it there than try and do it on the CPU and incur all that cost. So this is an exclusive scan, which means that I'm not including the final number. This is a way of doing the same thing, but with fewer operations, right? So this should be familiar. This is actually a reduce. It's exactly what we were doing before, right? I end up with my magic 136 up the top there. The difference you need to focus on here is that prior to this, when I showed you reduce, I didn't care about all the other intermediate numbers, right? I only cared about this final number that appeared in, the first, or in this case, the last index in my array. Everything else, was white. I didn't care about it. Here, I actually want all this other stuff. So this occurs in two steps. The first step of my scan is I do an upsweep. So I do a reduction. The second step is what's called the downsweep. The first thing I do in the downsweep is I zero out the top element of my array. So I throw away the total of my reduction. And here's where it gets complicated. And this is why we're not going to look at this in code. Question?
Can you go back one slide?
Sure.
Why is there is it just a mistake or am I confused? There's a 2 and a 3 on the first and second row for the second column. Why are those different? I think it's
Oh, that's a typo. I apologize. Imagine that is a 3. Okay? All the numbers persist up, right?
So which order of operations happening? Are they going up or down?
They're going up.
Okay.
Right, sorry, I've reversed it. I thought about not reversing it for the purposes of the talk, but everyone who describes the algorithm talks about an upsweep and a downsweep. So it just got more confusing, and it's challenging enough as it is. But yeah, well done for spotting the typo. Yeah, you probably get a small prize for that this early in the morning. And yes, this time we are going from bottom to top, for which I apologize, but it will become clear. So now I zero out that element. And now I'm going to go down again, right? So we're back in the world of the normal. And I'm going to do two things. The first thing I'm going to do is start adding elements with an ever-reduced stride. The second thing I'm going to do is swap or copy elements. So in this case, I've added element 7 and element 15. I get 36 because remember I already zeroed out the top element. And I'm going to copy element 15 into element 7. I claim no credit for thinking how you would do this, right? Someone way smarter than me thought this up. Which brings me to another point, is that there's lots of really great literature on this stuff. NVIDIA has done a fantastic job in writing white papers on this sort of stuff. I'm sure AMD has some too. There's lots of papers. GPU Gems has some stuff on this. If you're interested in this, I would before you tackle something, I would go and consult the literature, because this is not something you're going to come up with on a Friday afternoon and have done by Monday morning. So in my next set of operations, I'm going to use a stride of 4. I'm going to add and copy the next set of elements. Same again. And same again. And magically, we actually have the result we expect at the bottom, which is an exclusive scan. So the first element's always 0. The second element is going to be the first element multiplied by the result of the previous element. So the second element is 1 plus 0. Third element is 2 plus 1, which is 3, and so on and so forth. We don't have 136 because that would be the next element we didn't calculate. So that is a little bit like magic, right? But a lot of this stuff is really well written up. I implemented this as part of the AMP algorithms library. I found a couple of papers on the web. There's a NVIDIA white paper about it. I implemented a whole load of these algorithms based on those. But these are the sort of tricks and the way you have to think about it. So these diagrams are super useful, right? They really help you kind of get your head around what you're trying to do in the code before you write the code. And again, you shouldn't have to write scan, but you may need it because it's a really common building block of other GPU algorithms. The AMP algorithms library supports scan. I believe Thrust supports scan. There are probably other libraries that support scan too. There's been lots of research, lots of papers on how to write better, more efficient scans. We also have a DirectX scan wrapper. Scan is a primitive within the DirectX direct compute libraries. That's how important it is. People use it all the time. For instance, if we go back to our algorithm tree, you'll see here that if you want to do radix sort, you need scan, which is why I wrote scan, because I wanted to write radix sort. So just to sort of summarize, here are some of the things that we hopefully covered. I didn't get to really cover global memory access patterns, or global and tile static memory access in particular detail, but that's something else to think about. A lot of it's in the book. There are actually 2 chapters in the book. One goes through the reduction implementations I showed you, and a bunch of other implementations, like step by step, and explains a lot of what's going on here. There's also a chapter on performance, which covers a lot more of the sort of deep dark secrets and how to get the most out of your GPU. There's also AMP also supports, as does CUDA, supports some more graphics orientated things like textures, where you can use the GPU's texture memory, which in some cases can be advantageous. So what's next? So as I say, I've been working on this library. I'm about to do another release of it, which will have radix sort and another implementation of scan in it. I'm hoping to get out another version by the end of the year. The interesting thing here is, and if you've been in any of the other sort of talks on GPUs, you'll know that AMD are working on a port of C++ AMP to run on Clang and LLVM. That's actually been released now. They were nice enough to give me a GPU so that I can start porting to Linux. I'm actually really excited about that. I'll be honest, when Microsoft told me that C++ AMP was an open standard, I probably rather harshly mentioned the Office XML standard as another example of a Microsoft open standard. In fact, they've really come through on this one. There was a project by Intel called Shelvin Park, where they produced a proof of concept of the AMP runtime on top of OpenCL, and AMD have taken it and produced a version that they've released. I'm hoping to get the AMP library running on it. We're going to add some more features. I'd like to spend some time doing some tuning, but at the moment it's only me. If anyone fancies working on an open source GPU library, I'm open to offers. I like working on it. It's fun. It gives me a chance to kind of do some C++ that other people can enjoy, rather than just stuff I've done for me. If you want the book, they have copies outside on the bookstore. You can find all the source online. I actually completely rewrote all of the examples to be as modern C++ as I knew how. So that probably means they're not Herb Sutter level, but they won't make you cringe. I invested very heavily in that for both the books I wrote on C++. So you can download all the samples. As I say, the book's outside. It covers everything in this talk and a whole bunch more. There are other resources. The AMP team actually has a really good blog that covers a lot of that stuff. The HSA Foundation are the people who are producing the AMP port for Clang and LLVM. And there are a couple of forums. You can find me on the Stack Overflow forum quite a lot. If you ask a question about C++ AMP, I will probably answer it. And we have a couple of minutes for questions, I believe. Yes, 5 minutes for questions. There are a couple I'm not going to answer. Is the life on Mars? Is the standard model of physics correct? And what's the age of the universe? But other than that, I'm open. Yes, question at the front here.
What was the difference between using every other thread and you just use the beginning threads?
So the question is, what's the difference between using every other thread and using the beginning threads? So let me just see if I can find that slide. I want this slide, actually. So remember I talked about warps, right? So my algorithm divides everything up into blocks, or tiles, right? And they get scheduled on a GPU processor. Under the hood, the GPU is actually dividing things up into threads that run in groups or clumps, or NVIDIA calls them warps, right? When you run one of those threads, or one of those groups, everything in the thread kind of gets executed in lockstep, right? So if I have a thread where I'm doing both, where some of the threads have to execute one branch of a conditional and some threads have to execute the other branch of a conditional, then I have a problem, because effectively what I'm saying is all threads incur the cost of executing that conditional, whether they actually need to or not. Does that make sense?
I guess I was thinking that what you were showing was going to be one warp, but if it's actually multiple warps, then it makes sense.
Yes. So the problem is, my tile, I showed you 8 threads. What I should have shown you is 512, but PowerPoint isn't wide enough. So yeah, you've got to think about, I've not shuffled 4 down, and I've got like something that's 8 wide. I've got something that's 512 wide, and the first half, so 256 blocks that has loads of blocks of 32 in it. They all say, oh, my conditional is true. They execute the true branch, and they execute slightly slower. But remember, I'm scheduling them. So I'm throwing these things on, and they're executing. When I get to the ones where the conditional is false, they'll say, well, the conditional is false for all these things, so I can be that much faster. Whereas if I mix them up, I can't be. Another question?
Yeah, what if you just took the approach of don't even have a conditional, just have everyone execute, and then just don't disregard those results? Is that a valid GPU programming technique? So as opposed to having a conditional, everyone's just doing a stride, and then you have a bunch of garbage sentinel values over there, and everyone's just doing a add by 2, add by 2, add by 2, and it's like one of those things. Okay, those are incorrect results. I don't care. I'm not even going to use them next time.
You can do that. So the question was, well, what if I just have everyone execute the conditional and just ignore the junk, right?
They don't even execute the condition.
Right.
No condition. Just do it.
Oh, I see. You could do that. So just to have everybody do the work. And there are some cases where you do that, right? In this case, we're hoping that by not doing the add, we're actually going to be a bit faster, right? Because...
But if they all have to kind of stick to that point, then what's the point?
Well, no, the point is that the warp, if I have a conditional that evaluates the same for every thread in the warp, I can now skip that conditional, right? The compiler and the runtime can conspire with me to say, oh, all of these things are going to evaluate to false, so I don't have to execute the conditional. The problem occurs when some of the things execute the conditional and then some do not, right? And you can think about it as the threads that do, and the threads that don't still have to wait, right? So they're no faster, whereas I could have had all these threads off somewhere else where the warps were just going through much, much faster. Is that?
Yeah.
It's not easy, so I'm glad you asked the question.
Power consumption. If it can idle some warps. Right?
So the comment was, yes, would I get better power consumption if I could idle some warps? And the answer is yes. Lots of mobile processors today will idle warps and cores. It also turns out that with a lot of smaller processors, actually, you either want everything running flat out or everything doing, or as much as possible doing nothing, right? So when I write GPU code, I write it for performance. I'm trying to get everything to run flat out, and actually that's still a valid strategy with a smaller device where you're worried about power consumption. Question from the gentleman over there.
There is a standardization proposal to the standardization committee for the parallel algorithms. You might have heard about that.
Is this the parallel STL?
Parallel skills, yeah. And there we have an execution policy, which currently is sequential, parallel vectorized. Well, I could see that another execution policy would directly map onto the GPU without the user having to go through that array view thing and so on. So just doing it under the, is something planned to do that? I mean, I know that Microsoft has a open source implementation of that parallel STL, and you are doing open source work. Is that a connection that you use the project?
So the question was, the standards people are getting together to work on essentially the parallel STL, and how does that kind of map into this work, given that Microsoft has an open source implementation for parallel STL? Do I know anything about it? Essentially, no, I don't know anything about it. That's one of the things I've come to learn about a bit more this week. I actually know some of the people on the team that's doing some of that work. Just to be clear, I worked at Microsoft for 10 years. I never ever worked on that team or even in the same building. I just happen to know some of them. But yeah, I'm sort of hoping that the way forward for C++ AMP, if nothing else, is to influence where we take things in the future. I also know, for instance, there's a proposal for adding ArrayView to the standard as a way of abstracting n-dimensional arrays in a sort of a better way than what we have today, which is basically a 1D array that you can access in different ways. Does that answer the question? Sorry, I don't have any more insight than that today.
So the answer is no.
The answer is no. Yes. At the moment, it is no. But I know all those guys are involved in both of those projects. So
I would see big potential in that, because that would avoid people having to learn yet another C++ Amplish, or however it's called, language, and would open the door for good implementations for other things, and still be standards conforming.
Mm-hmm. Yes. I'm all about standards conformance. So I would like that to happen. I would like there not to be n different ways of programming GPUs, because it's kind of a play. Any other questions? Question over here.
It seems like to get optimal performance, you have to understand know its runtime, the underlying architecture of the GPU in order to get your tile sizes set exactly right. Is there any help in AMP for abstracting that away in some way, or it's just because you were talking about getting good performance, but it seems to me it depends on which GPU board you've got.
So the question was really, how would you get good performance in doing things like picking tile sizes without really understanding exactly what hardware you're on? So first off, I think AMP will give you reasonably good performance. At the end of the day, it doesn't matter what you're optimizing. If you really want to get the last ounce of performance out of it, you need to understand the hardware you're running on. When you do that, typically you will make it run faster on that piece of hardware and less fast on other pieces of slightly different hardware. The reality is, I'm sure if you really, really care about absolutely every single flop and you're prepared to go and commit to a vendor, right? You can go and buy a bunch of NVIDIA GPUs, you can write a whole bunch of CUDA code, and I suspect you can get it to run faster than C++ AMP. The problem is that that's the only place it's ever going to run, right? C++ AMP is like a lot of abstractions. You pay for that abstraction somewhere, right? So I think you're going to get pretty good performance out of C++ AMP. I think, when I target the library at people who want to get good performance out of their GPU, certainly in comparison with their CPU. I have not done a lot of performance work on that library, largely because I would rather focus on breadth than depth, right? Because I think that's where the audience is for this, right? But you're dead right. Picking tile sizes and stuff can be hardware dependent. We certainly saw some variations in different pieces of hardware running some of the things we did with, for instance, reduce on different hardware with different tile sizes, different drivers too can make a difference. But that's the world you live in if you kind of want to be targeting different pieces of hardware. I've got one more question at the back and then I think we're done.
Is that me?
That is you, yes sir.
All right. So I like Honda's question, but having been both world, the C++ and the GPU area through my OpenMP connections, I'd like to answer some of this question, but maybe not in here. But let me just say that the parallelism TS is talking about a sort algorithm. It does nothing about talk about memory movement and memory model, which is some of what AMP used to do and OpenMP does. And that missing part is actually a key ingredient to high performance GPU. Without that, it actually makes it very difficult for pure library implementation to understand how memory is placed. You mentioned things like, in some places you don't have to do the extra copy, in other places if you don't know, you're gonna do kind of bad things to it. So these are the big things I want to talk about, and I'll talk a little bit about that.
Okay. So the comment was there's another talk coming up on OpenMP where we talk a little bit about the challenges of writing more generic parallel algorithms when it comes to things like memory movement. I guess I would follow that with, if you care at all about performance, you better care about memory movement, right? It's all about memory, right? If the minute you miss cache, you're in a whole world of hurt, right? It's like if I asked you, what's the time in London? And you decided that you'd fly to London and ask someone. Right? No. Look it up on your phone. Okay, well, thank you very much. I hope you enjoyed it.